When we look up at the night sky, it feels immediate, as if the stars above us exist exactly as they are in this moment, fixed and quietly present. That feeling, however, is an illusion created by our senses. In reality, the universe never shows us the present, not even once. Every point of light we see in the sky is a memory, some only seconds old, others thousands or even billions of years old, carrying information from a time long before human civilization began. This isn't poetry or metaphor, but simple physics. Light doesn't arrive instantly. It travels at a finite speed, the fastest speed allowed in the universe, roughly 300,000 kilometers per second. That speed is unimaginably fast, yet still slow enough to turn the universe into a vast archive of its own history. When you look at the moon, you see it as it was about 1 second ago. When you look at the sun, you see it as it was just over 8 minutes ago. If the sun were to disappear at this very moment, the sky would remain bright and unchanged for those 8 minutes before darkness finally arrived. That short delay feels insignificant, but once we move beyond our solar system, the effect becomes profound. The nearest star system, Proxima Centauri, appears to us as it was more than 4 years ago. The light entering your eyes tonight left that star when the world was different, and events were unfolding that are already settled now. As we look farther into space, we are also looking deeper into time, because distance and time are inseparable in the universe. This means astronomy isn't simply the study of distant objects, it is the study of history itself. Telescopes don't only magnify space, they reveal the past. Every improvement in telescope technology allows us to collect light that has been traveling longer, carrying stories from earlier eras of the cosmos. This realization may seem simple at first, but its implications are profound, because it means there is no way to observe the universe as it exists right now beyond our immediate surroundings. The present moment exists only here, locally, while everything else we see is delayed by the journey of light. Even the stars in the same patch of sky aren't synchronized with one another. Each belongs to a different moment in cosmic history. The night sky isn't a snapshot frozen in time, but a collage assembled from many different eras. For most of human history, this was completely unknown. People believed the heavens were timeless and unchanging, a perfect realm beyond Earth. Stars were imagined as fixed points embedded in a crystal sphere, incapable of birth, change, or death. That belief survived not because it was true, but because humans lacked the tools to see otherwise. Everything began to change when we learned how to gather more light. The earliest telescopes were crude by modern standards, yet they shattered assumptions that had endured for thousands of years. When Galileo pointed his telescope toward the sky in the early 17th century, he wasn't attempting to look into the past, he simply wanted to see more clearly. But clarity has consequences. Galileo observed moons orbiting Jupiter, proving that not everything revolved around Earth. He saw imperfections on the sun, challenging the idea of celestial perfection. He detected stars too faint for the naked eye, revealing that the universe was far larger than previously imagined. What Galileo didn't realize was that he was also looking backward in time, even if only by small amounts. The starlight, he observed, had already been traveling for years or centuries before reaching his telescope. As telescopes improved, this backward glance grew deeper. Each new instrument gathered older light, carrying information from more distant and ancient regions of space. Astronomy quietly transformed into a time science. Unlike archaeology, which digs into the ground, astronomy digs into the sky. Instead of bones and artifacts, it uncovers photons. Each photon carries information about its origin, its journey, and the conditions it passed through. Light remembers. It remembers temperature, motion, and composition. Encoded within its wavelength and intensity are clues about distant environments and long-past events. By learning how to read light, astronomers learned how to read time. This is why distance matters so deeply in space science. Distance isn't merely a measure of how far away something is. It is a measure of how far back in time we are seeing. A galaxy 1 million light-years away appears as it was 1 million years ago. A galaxy 10 billion light-years away appears as it was 10 billion years ago. There is no assumption involved here, only geometry and physics. This leads to one of the most astonishing truths about the universe. The deeper we look into space, the younger the universe becomes. When astronomers point powerful telescopes toward the farthest reaches of the cosmos, they are not just observing distant objects. They are witnessing the universe as it existed shortly after its birth. In a very real sense, the sky contains a timeline. Nearby stars show the recent universe, distant galaxies reveal its youth. And the most ancient light shows the cosmos when it was still forming its first structures. The universe has preserved its own history, not in records or memories, but in motion. Time didn't erase the past. It carried it outward at the speed of light. Every direction we look represents a different chapter. On Earth, the past lies behind us and the future ahead. But in space, the past surrounds us. The universe stores its history across space itself. This is why modern astronomy requires patience. You cannot rush cosmic information or speed up light. You can only build better instruments and allow the universe to reveal itself at its own pace. Many of the photons collected by modern telescopes began their journey before Earth existed. Before the sun formed, before planets took shape. They traveled for billions of years through expanding space before ending their journey on a detector or in your eyes. Nothing we see in space is happening now from our perspective. Everything is delayed. Everything is archival. Yet this delay is not a flaw. It is a gift. Without it, we would never know the universe's past. Instead, light preserves history as an unbroken chain, allowing us to reconstruct where we came from and how the cosmos evolved. In the next part, we'll explore how astronomers learned to measure this cosmic timeline and how distance became a ruler for time itself. Thanks for watching. And don't forget to subscribe for more journeys into the cosmos. Objects at different distances. The stars nearby show us the recent past. Galaxies far away reveal an earlier era. And the most distant light imaginable shows us the universe in its infancy. The night sky became a history book, with each layer of distance representing a different chapter in time. But to read this history book, astronomers needed to be incredibly precise. Knowing that light takes time to travel wasn't enough. They had to know exactly how far away things were. Without accurate distances, the cosmic clock would be unreadable. And measuring distance in space is one of the hardest problems in science. Here on Earth, we can use rulers or GPS. But in space, there's nothing to measure against. So, astronomers got creative. They built what's called the cosmic distance ladder, a series of methods to measure farther and farther out into space. with each step building on the last. The very first rung of this ladder is called parallax. As the Earth orbits the Sun, nearby stars seem to shift their positions slightly against the backdrop of more distant stars. It's a tiny, tiny shift, but using simple geometry, it gives us the first reliable distances beyond our solar system. With these nearby distances measured, astronomers could calibrate other tools. They discovered a special type of star called a Cepheid variable. These stars pulse, getting brighter and dimmer in a regular rhythm. And here's the magic trick. The speed of their pulse is directly related to their true brightness. So, by measuring how fast a Cepheid pulses, astronomers know how bright it should be. They can then compare that to how bright it appears from Earth to calculate its distance. Cepheid variables became our cosmic mile markers, allowing us to measure distances across our galaxy and even to other nearby galaxies. This was a game changer. Suddenly, the universe got a whole lot bigger. Galaxies we thought were close turned out to be unimaginably far away. Could figure out how much space had expanded since the light left that galaxy, and therefore how old the universe was at that time. Distance, time, and expansion all merged into a single beautiful picture. The universe wasn't just a place anymore. It was a story. A story written not in words, but in light. Every single photon of light that reaches our telescopes carries information about where it came from, its temperature, its motion, its chemical makeup. And when astronomers learned to decode these signals, they gained the ability to read the chapters of cosmic history directly. Telescopes didn't just magnify things, they became time machines. As our telescopes got better, we started detecting light from galaxies so far away that their light had been traveling for billions of years. This light left its source when the universe was young, hot, and chaotic. Back then, galaxies were small and messy, forming stars at a furious pace. By comparing these young, distant galaxies to the mature ones we see nearby, astronomers could literally watch evolution unfold across cosmic time. It was like seeing the entire lifespan of the universe, frozen in layers of light. Of course, each new observation brought new questions. Why did galaxies change shape over time? Why did star formation slow down? The answers were hidden in the faintest, most distant light. To capture it, we had to send our telescopes into space. Earth's atmosphere blurs and blocks a lot of light. But space-based telescopes, like the Hubble Space Telescope, changed everything. Hubble gave us an unprecedentedly clear view of the distant universe. It saw galaxies so far away that their light was more than 13 billion years old. These images confirmed that the universe was evolving, growing more structured over time. But Hubble also found something totally unexpected. The expansion of the universe wasn't slowing down as everyone thought it would. It was accelerating. This implied some kind of mysterious force, now called dark energy, was pushing everything apart. Once again, measuring distance reshaped our understanding of time and the fate of the cosmos. Other telescopes joined the hunt. Infrared telescopes could see through cosmic dust and detect light that had been stretched all the way into the infrared spectrum. Radio telescopes mapped the cold gas where new stars are born. Each new type of telescope added another layer to our cosmic story. And then we found the oldest light of all, the cosmic microwave background of the Big Bang itself, an echo from a time when the universe was only 380,000 years old, long before the first stars or galaxies even existed. The cosmic microwave background is the earliest chapter of the universe we can possibly read. Before that time, the universe was so hot and dense that it was opaque. Light couldn't travel freely. This glow marks a boundary, a horizon in time that we can't see past, no matter how powerful our telescopes become. It's a reminder that even though we've learned so much, the universe still holds some of its earliest secrets. But what an incredible story it has told us so far. From a hot, dense beginning to the formation of stars, galaxies, and eventually us. All of this is possible because of one simple, profound idea: that distance is time, that light carries memories. To observe the sky is to have a dialogue with the past. But this cosmic horizon isn't the only limit we face. There are regions of the universe we will never see, no matter how long we wait. Join me next time as we explore the ultimate boundaries of observation and why the speed of light means some parts of the universe's story will forever remain untold. Thanks for watching, and don't forget to subscribe for more cosmic journeys. As distance became time and space turned into a cosmic clock, astronomers encountered an unexpected boundary. No matter how powerful their instruments became, there was a limit beyond which the universe refused to reveal more. This limit wasn't created by technology, ignorance, or lack of effort. It was written into the structure of reality itself. It was the horizon. Walk forward, and the horizon moves with you. In space, horizons behave very differently. They are not lines you can cross to see more. They are limits defined by time, motion, and the speed of light. They don't retreat when you advance. They simply exist. The most fundamental horizon in cosmology is the observable universe. This is not the entire universe. It is only the part from which light has had enough time to reach us since the beginning of cosmic expansion. Everything beyond that boundary may exist, but it is causally disconnected from us. No signal from there has arrived yet, and no signal we send can reach it. This idea feels abstract, but its cause is straightforward. The universe has a finite age. Light travels at a finite speed. Combine these two facts, and a boundary appears naturally. The observable universe is a sphere centered on us, not because we are special, but because observation always centers on the observer. Every observer, anywhere in the universe, has their own observable sphere. This means the universe has no single privileged viewpoint. There is no cosmic center. Every location experiences its own horizon. What we can see is limited not by position, but by time. This realization reshaped cosmology. For centuries, humans assumed that with enough technology, everything could eventually be seen. Horizons shattered that assumption. They revealed that some information is not hidden, but unreachable. It has not had time to arrive. Even more unsettling is the fact that the observable universe is not static. As time passes, light from more distant regions reaches us, slowly expanding what we can see. At the same time, cosmic expansion accelerates, pushing distant regions away faster and faster. Some regions that are visible today will eventually slip beyond reach forever. This introduces a second horizon, known as the cosmic event horizon. It marks the boundary beyond which events will never affect us, no matter how long we wait. Light emitted beyond this horizon today will never arrive, because space itself expands too quickly in between. The universe, in this sense, is not only vast, it is selective. It reveals some chapters of its story and withholds others permanently. This is not a limitation of intelligence or curiosity. It is a limit imposed by geometry and expansion. The universe does not owe us completeness. Understanding horizons forces humility. There are questions we can ask but never answer. There are regions that exist but remain forever silent. Not because they choose silence, but because physics enforces it. This silence does not make those regions meaningless. It simply places them beyond interaction. Meaning, like observation, is local. Horizons also reshape how we think about beginnings. When astronomers detect the cosmic microwave background, they are observing a surface of last scattering, a time when the universe became transparent to light. Before that moment, the universe was opaque. Light could not travel freely. The microwave background forms a horizon in time, beyond which electromagnetic observation cannot reach. No telescope, no matter how advanced, can see past that surface using light. To access earlier times, astronomers rely on indirect signals such as neutrinos or gravitational waves. Even these have limits. The earliest moments remain inaccessible, not because they are forbidden, but because no messenger survives from that era. This introduces a profound idea. Knowledge is constrained not just by what exists, but by what can carry information forward. The universe communicates through messengers. Light is the most familiar, but not the only one. Each messenger has a range, a lifespan, and a limit. Gravitational waves, ripples in space-time itself, offer a different channel. They pass through matter almost unhindered. They can carry information from regions light cannot penetrate. In principle, they could reveal events closer to the beginning of time. Yet even gravitational waves face a horizon. There is a limit to how far back they can be traced. No matter which messenger we choose, a boundary remains. There is always an edge to what can be known. Horizons also exist at smaller scales. Black holes possess event horizons of their own. Once information crosses that boundary, it cannot return to influence the outside universe. From the outside, the interior becomes unknowable. Physics does not forbid what happens inside. It simply prevents us from learning about it. This parallel is not accidental. Horizons are a general feature of space-time. Whenever gravity, motion, and finite signal speed interact, horizons appear. They divide reality into accessible and inaccessible regions. This challenges a deep assumption about science. Horizons reveal that total knowledge is not possible, even in principle. The universe is not fully readable. It is partially legible. This does not diminish science. It defines its scope. Within horizons, understanding can be deep, precise, and predictive. Beyond them, speculation remains untestable. The distinction matters. Science progresses by respecting boundaries as much as by pushing them. Horizons also influence the arrow of time. Because information cannot cross certain boundaries, the future and past are not symmetric. Some correlations can be formed, others cannot. Time gains direction from the loss of access to information. This connects back to entropy. As the universe expands and horizons grow, information becomes spread across ever larger regions. Some correlations are lost forever. This loss is not destruction, it is separation. Information still exists, but cannot be reassembled. From our perspective, this feels like forgetting. The universe forgets parts of itself, not by erasing them, but by making them unreachable. This forgetting shapes cosmic fate. As expansion accelerates, galaxies beyond a certain distance fade from view. Eventually, even nearby galaxies will disappear over the horizon. Future observers may see only their local group, unaware that a vast universe once surrounded them. This future ignorance is not due to lack of intelligence. It is due to horizon dynamics. This leads to a sobering realization. What we observe now is privileged, not because we are special, but because we live at a particular time. We exist early enough to see far, but late enough to see structure. This window will not remain open forever. Understanding horizons gives urgency to cosmology. The universe is not slowly revealing itself indefinitely. It is revealing itself temporarily. Some information is available now that will not be available later. This urgency does not require panic. It invites attentiveness. Horizons also offer a strange comfort. They remind us that mystery is not failure, it is structural. Not knowing everything is not a temporary shortcoming. This perspective reframes humility as accuracy. Accepting limits is not giving up. It is understanding reality as it is. In the next part, we will explore how the universe uses expansion itself to shape structure, how matter organizes under gravity despite cosmic stretching, and how large-scale patterns emerge even as horizons grow. The universe does not simply expand into emptiness. It organizes as it unfolds. Thanks for joining us, and we'll see you in the next one. One seems to destroy structure, the other to build it. But the universe didn't choose between them. It let both happen at the same time. And from this quiet battle, the largest structures ever known were born. In the very early universe, matter was spread out almost perfectly evenly. There were tiny, tiny differences in density, but they were incredibly subtle. Yet these tiny imperfections were the seeds of everything. Grow. It didn't stop them completely. Regions that were dense enough had enough gravitational pull to overcome the stretch of expansion and began to collapse inward. The regions that weren't so dense just became emptier and emptier. Slowly but surely, the universe began to organize itself. This organization wasn't random at all. It followed a very specific geometry. Matter started flowing along invisible pathways, like streams merging into rivers. These streams of matter formed long filaments and vast, flat sheets, all of which connected at dense intersections, or nodes. These nodes are where galaxies and massive clusters of galaxies were born. The vast, empty regions between these filaments became what we call cosmic voids. Altogether, this incredible network of filaments, nodes, and voids forms what astronomers call the cosmic web. And the cosmic web isn't just a cool-sounding name. It's a real, measurable structure that spans the entire observable universe. If you look at a map of the universe, you'll see that galaxies aren't just scattered around like salt sprinkled on a table. They trace out these glowing filaments, some stretching for hundreds of millions of light years, And in between these filaments are those enormous, dark voids, regions with almost no galaxies at all. This incredible pattern repeats itself on every large scale we can observe. What makes this so mind-blowing is that this intricate web grew from a universe that was almost perfectly smooth. The early universe was uniform. The universe today is a complex cosmic tapestry. Gravity, working over billions of years, turned those tiny initial differences into a grand cosmic architecture. A key player in this whole story is dark matter. Unlike the normal matter that makes up stars, planets, and us, dark matter doesn't interact with light at all. It's completely invisible. But it does have gravity. In fact, most of the gravity in the universe comes from dark matter. It built the scaffolding for the cosmic web. Dark matter collapsed first, creating deep gravitational wells. Normal gas was then pulled into these wells, where it cooled down and ignited to form the first stars and galaxies. So, the galaxies we see are like lights on a Christmas tree, lighting up the invisible structure that dark matter built first. Even the biggest structures, galaxy clusters, are found at the most massive nodes in this web. So you have this fascinating balance. Expansion dominates on the largest cosmic scales, pushing everything apart, while gravity dominates locally, pulling things together. Huge, round, elliptical galaxies were born from violent collisions. The filaments persisted, and the voids grew even emptier. Think about it. The universe became more structured and more empty at the same time. This duality is what defines the history of the cosmos. Expansion makes the empty spaces bigger, while gravity makes the dense places denser. The voids aren't just failed attempts at making structure. They are a fundamental part of it. As matter flows out of them and toward the filaments, the voids get bigger and emptier. Looking into the far future, voids will take up most of the volume of the universe, with all the matter concentrated into isolated islands of galaxies. By studying the cosmic web today, astronomers can actually predict this future. We can see how clusters will merge, how filaments will thin out, and how voids will continue to expand. Eventually, each gravitationally bound region, like our own local group of galaxies, will become an isolated island universe, cut off from all others by the vastness of expanding space. But the web isn't just about position and motion. It also affects temperature and energy. These powerful processes control how fast stars can form and how galaxies grow. The universe is a dynamic, interconnected system where everything affects everything else. It took a long time and a lot of patience to discover this. Early telescopes couldn't see the big picture. What we see is just one patch of a much larger, perhaps infinite, pattern. The emergence of the cosmic web teaches us a profound lesson. The universe doesn't need a grand designer to create order. With just a few simple rules, like gravity and expansion, and enough time, incredible complexity appears all on its own, and that doesn't make it any less wondrous. If anything, it makes it more so. This vast, intricate, and beautiful structure wasn't built. It grew, and it's still growing and changing today. The web is not a static object. It's a living, evolving process. Filaments shift, clusters grow, and voids expand. The story of the cosmos is far from over. Now that we've seen the grand stage, the cosmic web itself, next time we'll zoom in and explore the actors on that stage, the galaxies. Galaxies began their long and complicated lives. The earliest galaxies were small and chaotic. Gas collapsed into deep wells of dark matter and ignited furious bursts of star formation. These young systems looked nothing like the smooth disks and elegant spirals we see today. They were just jumbled clumps of stars and gas, frequently colliding and merging. You see, the early universe was a crowded place. Galaxies lived close together, and encounters were common. Every single interaction left its mark. When galaxies passed near one another, gravity distorted their shapes, pulling out long, beautiful streams of stars and gas called tidal tails. Sometimes, galaxies would merge completely, combining all their stars and gas into one single, larger system. These mergers weren't rare events. They were a primary driver of how galaxies grew. As they merged, their stars mixed, their gas clouds collided, and their internal motions were completely rearranged. Some mergers were gentle, allowing new disks to survive and reform. Others were violent, scrambling stellar orbits and destroying any ordered motion. Spiral galaxies, like our own Milky Way, emerged where rotation was the dominant force. Gas settled into thin, spinning disks around a central bulge. It's important to know, these arms aren't rigid structures. They're more like traffic jams patterns moving through the disk as stars flow in and out of them. Elliptical galaxies, on the other hand, formed very differently. Major mergers completely disrupted rotation and randomized the orbits of stars. The result was a smooth, rounded, almost featureless system. Instead of being supported by orderly spin, they're held up by the random motions of their stars. Ellipticals often formed in dense environments, like galaxy clusters, where interactions were frequent and much more energetic. And that brings us to a key point: environment matters. Galaxies did not evolve in isolation. But galaxies trapped inside massive clusters faced a much harsher fate. These clusters are filled with incredibly hot gas, and as galaxies moved through it, this gas would strip away their own cold gas supply. Essentially, galaxies aged much faster in these crowded neighborhoods. This process, known as quenching, transformed once active, star-forming galaxies into quiet, red and dead systems dominated by old stars. So, the universe gradually shifted from a youthful era of intense star formation to a calmer, more mature phase. But this transition didn't happen everywhere at once. It unfolded unevenly, shaped by a galaxy's location and its unique history. Young galaxies glow, a brilliant blue, dominated by hot, massive stars that burn brightly but die very quickly. Older galaxies appear much redder, as those massive stars have vanished, leaving behind only the cooler, longer-lived ones. So, in a way, a galaxy's color became a record of its age, and its shape became a record of its experience. Yet, galaxies weren't just passive victims of their environment. Internal processes mattered too. Star formation itself releases a tremendous amount of energy. Supernova explosions heat up gas and can drive powerful winds that blow material right out of the galaxy. And at the very center of most galaxies, supermassive black holes grew, influencing their entire surroundings. This energy heats the surrounding material, slowing down or even halting star formation. Galaxies, in a sense, learn to find a balance. Too much star formation would consume their fuel too quickly. Too little would leave them dim and inactive. But despite this apparent stability, change never truly stopped. Galaxies continued to merge, to accrete gas from their surroundings, and to respond to their environment. Even today, our own Milky Way is not finished evolving. It's currently absorbing smaller satellite galaxies, and, in about 4.5 billion years, is set to merge with our neighbor, Andromeda. That cosmic collision will reshape both systems into something entirely new. The amazing thing is, we can see this long evolution unfold because of light's finite speed. But when we look at distant galaxies, we're seeing light that has traveled for billions of years, showing us what they were like in their youth. By comparing them, astronomers can reconstruct these evolutionary pathways. It tells us that galaxies aren't different species. They are simply different ages, seen at different stages of their lives. This perspective completely transforms how we classify them. Spirals, ellipticals, and irregulars aren't fixed categories. They are stages, the outcomes of particular histories. Change the environment, change the merger rate, or change the gas supply, and the outcome changes. As galaxies continue to age, star formation declines, gas becomes scarce. Their stellar populations grow old, and the universe, as a whole, gradually dims. This dimming isn't sudden. It unfolds over tens of billions of years, but it has a clear direction. The era of bright, abundant star birth is temporary. Understanding how galaxies evolve reveals a deeper truth about our universe. It is not a static piece of architecture. It is a story of constant transformation. Structures form, mature, and eventually fade. Nothing remains unchanged forever. This realization prepares us for an even larger question. If galaxies age and star formation slows down, what does this mean for the future of the universe as a whole? Does this structure persist indefinitely, or does the expansion of space eventually win completely? In our next video, we'll step beyond galaxies to explore the role of dark energy, that mysterious influence accelerating cosmic expansion, and how it is reshaping the long-term fate of everything we've discussed so far. Thanks for watching, and be sure to subscribe so you don't miss it. For most of the last century, we thought we had the universe figured out, at least in broad strokes. Gravity, the force that keeps our feet on the ground and planets in orbit, was the master of the cosmos. Astronomers believed the universe's expansion, which started with the Big Bang, must be slowing down. Think about it. If you throw a ball into the air, gravity pulls it back down. It made perfect sense that the gravitational pull of all the galaxies on each other would act like a brake, gradually slowing down the expansion, maybe even pulling everything back together in a distant future. This was the comfortable, predictable view. Gravity attracts. Expansion should fight against it. But science is full of surprises. And in the late 1990s, one of the biggest surprises in modern history arrived. Two teams of astronomers were studying distant supernova, the explosive deaths of massive stars. These explosions are incredibly bright, so bright they can be seen across billions of light years. By measuring their brightness and how their light has been stretched by the expansion of space, we can figure out how fast the universe was expanding at different times in its history. What they found was completely shocking. The universe wasn't slowing down at all, it was speeding up. Galaxies weren't just drifting apart, they were being pushed away from each other, faster and faster with every passing moment. This was like throwing a ball into the air and watching it accelerate into the sky on its own. It defied everything we thought we knew. This mind-bending discovery meant there had to be some kind of invisible influence, a mysterious force working against gravity on the largest scales. Scientists gave it a name that sounds like it's straight out of science fiction: dark energy. It's not called dark because it's black or shadowy, but because we have absolutely no idea what it is. Its nature is one of the biggest mysteries in all of science. So what do we know about this strange phenomenon? Well, we know what it's not. It's not like ordinary matter, the stuff that makes up stars, planets, and us. It doesn't clump together to form structures. Instead, dark energy seems to be a property of space itself. It's a kind of energy inherent in the vacuum of the cosmos. And here's where it gets even weirder. As space expands, more space is created. And since dark energy is a property of space, more dark energy comes into existence. This creates a cosmic feedback loop. The expansion of space creates more dark energy, and that new dark energy pushes space to expand even faster. It's a runaway process, an endless acceleration that is fundamentally reshaping our universe. To put its power into perspective, let's look at the cosmic energy budget. Everything we can see and touch, all the stars, galaxies, and gas clouds, makes up only about 5% of the universe. Another 27% is dark matter, another mysterious substance that we can only detect through its gravitational pull. That leaves a staggering 68% for dark energy. Think about that for a second. More than 2/3 of our entire reality is driven by something we can't see, can't touch, and can't explain. Now, don't worry, dark energy isn't going to tear you apart. On small scales, like within our solar system or even our galaxy, gravity is still the boss. It's much stronger over short distances, so it keeps planets in orbit and stars bound together in galaxies. But on the vast intergalactic scales, dark energy wins. It overwhelms gravity, dictating the ultimate fate of the cosmos. As this acceleration continues, something strange happens to our view of the universe. Distant galaxies are receding from us faster and faster. Eventually, galaxies beyond a certain point will be moving away from us faster than the speed of light. Now, this doesn't break Einstein's laws, because it's not the galaxy itself moving through space that fast. It's the space between us and the galaxy that's expanding. The consequence is chilling. The light from those galaxies will never reach us again. They will effectively vanish from our sky, one by one. This creates what we call a cosmic horizon, a boundary beyond which the universe becomes forever inaccessible to us. Over billions of years, this horizon will appear to shrink as more and more galaxies cross that point of no return. Imagine the night sky in the far, far future. It will be a much lonelier place. Future observers in a galaxy like our own might only see their local cluster of galaxies. The countless other island universes we see today will have faded into an eternal, unreachable darkness. Future astronomers might even conclude that their galaxy is all there is, because the primary evidence for the Big Bang and cosmic expansion will have literally disappeared from view. So, what could dark energy be? The leading idea is something called the cosmological constant. This was an idea Albert Einstein himself came up with, though for a different reason. He later called it his biggest blunder, but it turns out he might have been right all along. This theory suggests that empty space, a perfect vacuum, isn't truly empty. It has a tiny, constant amount of energy inherent to it. As space expands, this energy density doesn't dilute like matter does. Its total influence just keeps growing, pushing everything apart. Another possibility is that dark energy isn't constant at all. It could be a dynamic field that changes over time, sometimes getting stronger, sometimes weaker. This opens up some wild possibilities for the universe's ultimate fate. For now, our best observations suggest that dark energy behaves like a constant. But even small deviations from that could lead to dramatically different futures. If dark energy remains steady, as it seems to be, the universe will expand forever. It will become colder, darker, and emptier. Galaxies will become isolated islands in a vast, dark ocean. Star formation will eventually cease as the gas runs out. The universe will enter a long, dark era of cosmic twilight, populated only by the fading remnants of dead stars. But what if dark energy grows stronger over time? This leads to a scenario known as the Big Rip in this cosmic horror story. The accelerating expansion becomes so powerful that it overwhelms all other forces. First, it would pull galaxy clusters apart. Then, it would tear galaxies themselves to shreds. Stars and planets would be ripped from their orbits. Eventually, even the forces holding atoms together would fail, and the very fabric of matter would be torn asunder in a final, violent end. There's also the chance, though less likely based on current data, that dark energy could weaken or even reverse its push. If that happened, gravity could once again become the dominant force on a cosmic scale. The expansion would slow down, stop, and then reverse. The universe would begin to contract, heading for a big crunch, a fiery cosmic collapse back into a hot, dense state, perhaps leading to a new Big Bang. What's so profoundly unsettling about dark energy is that it acts on space itself. It doesn't care about mass or what something is made of. It reshapes reality at its most fundamental level, and yet we can't directly detect it. We only see its ghost, its effect on the grand cosmic ballet of galaxies. No experiment has ever isolated a particle of dark energy. It is a force inferred, not observed. This vast gap in our knowledge is a humbling reminder that we are just beginning to understand the true nature of reality. Dark energy sits at the frontier of physics, a signpost pointing toward a deeper theory we haven't yet discovered. Yet, it also brings a strange kind of coherence to our observations. It explains the accelerating expansion, the large-scale structure of the cosmos, and why the universe looks the way it does. We happen to live in a very special cosmic era. For billions of years, matter and gravity dominated, allowing galaxies and stars to form. Now, we are in a transitional period where the influence of matter is waning, and the dominance of dark energy is just beginning. It's a brief window in cosmic history where the sky is still full of galaxies, and we have just enough information to piece together the story of the universe's past and future. Unlocking the secrets of dark energy is one of the greatest challenges for science in the 21st century. It will require new, more powerful telescopes, mapping the positions and movements of millions of galaxies with unprecedented precision. Each new piece of data adds to the puzzle, helping us refine our theories and test our predictions. Will we find that dark energy is Einstein's constant? Or will we discover something even more unexpected, something that points to new physics beyond our current understanding? For now, dark energy remains the quiet, invisible force pulling the universe apart, shaping the destiny of everything that is, was, and ever will be. It is a profound mystery, a cosmic question mark hanging over our heads. Thank you so much for joining me on this journey to the edge of knowledge. If you found this as fascinating as I do, make sure to like this video, subscribe to the channel, and hit that notification bell so you don't miss our next exploration. In our next episode, we'll journey from the largest scales of the cosmos to the most extreme objects within it, black holes. See you then. While dark energy quietly stretches the universe apart, gravity still performs its most dramatic work in places where matter becomes unimaginably dense. Nowhere is this more extreme than in black holes. These objects represent gravity pushed to its absolute limit, regions where space and time themselves lose their usual meaning. A black hole begins its life as a massive star. When such a star exhausts its nuclear fuel, it can no longer support itself against gravity. The core collapses inward with unstoppable force. If the remaining mass is large enough, no known force can halt the collapse. The result is a black hole, an object so dense that its gravity creates a boundary beyond which nothing can escape. This boundary is called the event horizon. It is not a physical surface, but a point of no return. Cross it, and all possible paths lead inward. Light cannot climb back out. Time itself behaves strangely near this edge, slowing dramatically from the perspective of an outside observer. At the center lies the singularity, a region where density becomes infinite and our equations break down. Physics, as we know it, cannot fully describe what happens there. The singularity marks the limits of our understanding. Black holes are often imagined as cosmic vacuum cleaners, devouring everything nearby. In reality, they are more subtle. A black hole exerts gravity, just like any other object of the same mass. If the Sun were replaced by a black hole of equal mass, Earth's orbit would remain unchanged. This radiation makes black holes visible indirectly, even though they emit no light themselves. These jets can extend for thousands, or even millions of light years, shaping entire galaxies. These giants contain millions or billions of times the mass of the Sun. They formed early in cosmic history and grew alongside their host galaxies. Their presence influences star formation, gas flows, and galactic structure. Despite their size, supermassive black holes occupy relatively small regions. The one at the center of the Milky Way, Sagittarius A*, has a mass of about 4 million suns, yet its event horizon is smaller than Mercury's orbit. Such density defies intuition. Black holes challenge our understanding of time. To a distant observer, an object falling toward the event horizon appears to slow down and fade, never quite crossing. To the falling object, nothing special happens at the horizon. It passes through in finite time. Both perspectives are correct, highlighting how time is relative. Inside the event horizon, the roles of space and time reverse. Moving forward in time means moving closer to the singularity. Escape becomes impossible, not because of force, but because of geometry. For decades, black holes were theoretical curiosities. Then evidence accumulated. Stellar motions revealed invisible masses. X-ray emissions betrayed accretion disks. Gravitational waves confirmed black hole mergers. Ripples in space-time itself detected here on Earth. These mergers showed that black holes can collide and combine, releasing enormous energy. Each detection opens a new window on the universe. Black holes also raise profound questions about information. When matter falls in, does its information disappear? Quantum mechanics insists information cannot be destroyed. General relativity seems to say it can. One proposal suggests that information is encoded on the event horizon itself, smeared across its surface. Another suggests it escapes slowly through subtle quantum effects. By regulating gas flows and triggering star formation, they help shape galaxies. Without them, the universe might look very different. There is even evidence that black holes played a role in the early universe, influencing how structures formed. Some theories suggest primordial black holes could have formed shortly after the Big Bang, possibly contributing to dark matter. At the same time, black holes remind us of limits. There are regions we cannot observe directly. There are questions we cannot yet answer. They mark the boundary between known physics and the unknown. Yet progress continues. With better telescopes, more precise detectors, and deeper theories, black holes are becoming laboratories rather than mysteries. Each observation brings clarity, even as new questions emerge. Black holes show us that gravity can dominate absolutely, bending reality to its will. But they also coexist with dark energy, which operates in the opposite direction. Together, these forces shape the universe's past, present, and future. In the next part, we will explore how black holes merge, how gravitational waves reveal these events, and how space-time itself can vibrate like a cosmic instrument. For most of human history, the universe was known only through light. Stars shone, galaxies glowed, telescopes gathered photons and turned them into stories. But light is not the only messenger. In the deepest language of the cosmos, space itself can move, stretch, and ripple. Those ripples are called gravitational waves. Gravitational waves are vibrations in space-time caused by the motion of massive objects. When something extremely heavy accelerates, space-time responds, not with sound or light, but with subtle waves that travel outward at the speed of light, carrying information about their source. For decades, these waves existed only in equations. Albert Einstein predicted them in 1916 as a consequence of general relativity. Even he doubted they would ever be detected. The effect was simply too small. By the time a gravitational wave reached Earth, it would stretch and compress space by less than the width of an atom. Yet, in 2015, humanity heard space-time for the first time. Two black holes, each many times more massive than the Sun, spiraled toward each other and merged over 1 billion light-years away. In the final fraction of a second, they released more energy than all the stars in the observable universe combined. That energy did not arrive as light. It arrived as a ripple. When that ripple passed through Earth, it gently stretched and squeezed space-time. Instruments called interferometers detected the change. The signal lasted less than a second, but it confirmed something extraordinary. Space itself can vibrate. Gravitational waves do not travel through space. They are distortions of space. As they pass, distances change slightly. One direction stretches, the perpendicular direction compresses, then the pattern reverses, back and forth, a cosmic rhythm. Detecting these waves required precision beyond intuition. The detector's measure changes thousands of times smaller than a proton. They must remain isolated from seismic noise, thermal motion, and even passing trucks. The fact that detection was possible at all is a triumph of human engineering. What makes gravitational waves powerful is what they reveal. They carry direct information about extreme events that produce little or no light. Black hole mergers, neutron-star collisions, possibly even signals from the early universe itself. When two black holes merge, light often cannot escape, but space-time always responds. Gravitational waves reveal the masses, spins, and energies involved. They confirm predictions of relativity under conditions that cannot be recreated on Earth. These detections have shown that black hole binaries are common. They exist throughout the universe. They form, evolve, and collide regularly. Each merger reshapes space-time locally and sends waves outward across cosmic distances. Gravitational waves also revealed something unexpected. Some black holes are heavier than models predicted. Others spin rapidly. Their origins challenge assumptions about how stars evolve and die. Each detection refines our understanding. In 2017, another milestone occurred. Two neutron stars collided. This time, both gravitational waves and light were observed. This was multi-messenger astronomy. Space vibrated. Telescopes lit up across the spectrum. Heavy elements like gold and platinum were forged in the collision. This event confirmed that neutron star mergers create many of the universe's heaviest elements. The atoms in your jewelry were born in space-time storms like this. Gravitational waves allow us to measure distances independently of traditional methods. They act as standard sirens. By comparing the signal strength to the waveform, astronomers can calculate how far away the event occurred. This provides a new way to measure cosmic expansion. In the future, gravitational wave observatories will become more sensitive. They will detect smaller events, more distant mergers, continuous backgrounds created by countless overlapping sources. Some waves may come from supermassive black hole mergers at galactic centers. These events unfold slowly over years. Their waves stretch space-time on scales larger than solar systems. Other waves may come from the early universe itself. If space-time underwent violent transitions shortly after the Big Bang, those motions may still echo faintly today. Detecting them would give us direct information about conditions moments after time began. Gravitational waves change how we think about silence. Space is not quiet. It carries memory. It responds to motion. It stores the imprint of massive events long after light has faded. They also reveal unity. Space and time are not passive stages. They are active participants. Matter tells space-time how to curve. Space-time tells matter how to move. And sometimes, space-time sings. This new way of observing the universe does not replace light. It complements it. Together, they form a richer picture. Light shows us surfaces. Waves show us motion. Light shows aftermaths. Waves show the act itself. We are still at the beginning. Gravitational wave astronomy is young. Most signals remain undetected. Most sources remain theoretical. But already, this new sense has transformed cosmology. It reminds us that reality is deeper than appearance, that the universe communicates in multiple languages, and that some of its most powerful messages arrive not as images, but as whispers in the fabric of existence. In the next part, we will explore how galaxies grow, collide, and evolve over billions of years, and how their quiet motions shape the cosmic web itself. Thanks for watching, and don't forget to subscribe for more journeys into the cosmos. When you look up at the night sky, everything seems so still, so permanent. Those distant galaxies look like frozen swirls of light, timeless and unchanging. But that's just an illusion created by immense distance and time. In reality, the universe is alive. Galaxies are in constant, slow motion, drifting, rotating, and dancing with each other across billions of years. The cosmos isn't a static photograph. It's a grand, evolving masterpiece, a slow architecture taking shape. This whole cosmic story began with tiny, almost imperceptible ripples in the very early universe. Think of it like a perfectly smooth pond. with just a few small disturbances. Gravity took hold of these tiny differences in density. Regions that were just a little bit denser started pulling in more and more matter. Over millions of years, this gravitational snowball effect formed the very first stars, which then clustered together to create the first galaxies. But these newborn galaxies didn't just pop up randomly. Gravity is the ultimate connector. It linked them together, pulling them into groups and then into massive clusters. These clusters aren't isolated either. They're connected along vast, invisible filaments of dark matter and gas, creating a breathtaking structure we call the cosmic web. Imagine a spider's web stretching across the entire observable universe. The galaxies are like dewdrops, clinging to its threads. In between these glowing filaments are enormous empty regions called voids, places with almost no matter at all. What's fascinating is that this web isn't made of anything we can see. Its structure is primarily shaped by dark matter, a mysterious substance that outweighs all the regular matter, all the stars, planets, and gas, by about 5 to 1. Dark matter doesn't emit or absorb light, so we can't see it directly. Its presence is revealed only through its powerful gravitational pull. It forms invisible halos around galaxies and clusters, acting like a hidden puppeteer, guiding their movements and growth. Honestly, without dark matter, the beautiful galaxies we see today simply wouldn't exist. Within this grand cosmic web, galaxies are constantly on the move. They travel at speeds of hundreds of kilometers per second. Now, that sounds incredibly fast, but on a cosmic scale, it's a gentle drift. Over billions of years, these slow, persistent movements completely reshape the universe. And sometimes, galaxies get a little too close for comfort. They pass by each other, and their mutual gravity wreaks beautiful havoc. Tidal forces can stretch out their spiral arms, creating long, ethereal tails of stars. Clouds of gas get squeezed together, triggering spectacular bursts of new star formation. And over even longer timescales, they can merge completely. A galaxy merger isn't a violent crash like a car wreck. The distances between individual stars are so vast that head-on collisions are incredibly rare. Instead, it's a gradual, gravitational embrace. The two galaxies slowly blend together. Stars from both systems settle into new, often chaotic orbits around a new common center. Their gas clouds, however, do collide, igniting a flurry of new star birth that can make the merged galaxy shine brilliantly. Our own Milky Way is a veteran of these mergers. It has swallowed up smaller galaxies many times over its long history. Astronomers can actually see the evidence of these ancient cosmic meals. Long streams of stars wrapping around our galaxy's halo are the leftover breadcrumbs, the remnants of those devoured systems. And we're on a collision course for our biggest merger yet. In about 4 billion years, our Milky Way is set to merge with our nearest large neighbor, the Andromeda Galaxy. This cosmic event will unfold over hundreds of millions of years. From our perspective here on Earth, it will be a slow, subtle transformation. The night sky will gradually change as the familiar constellations are replaced by a new tapestry of stars from Andromeda. But don't worry, our solar system will likely be just fine. The planets will remain in their orbits, and the sun will continue its journey just within a much larger, brand new galaxy. A galaxy's life is also shaped by its neighborhood. Those living in crowded, dense clusters are very different from the loners out in the cosmic voids. In a cluster, a galaxy is constantly moving through a sea of hot gas. This gas can act like a powerful wind, stripping the galaxy of its own star-forming material. Without that fuel, star formation grinds to a halt, and the galaxy becomes what astronomers call red and dead, filled with old, red stars and no new blue ones. In contrast, an isolated galaxy can keep making stars for much longer. It's constantly fed by fresh gas flowing in along the filaments of the cosmic web, like a river delivering nutrients. New stars ignite, and its beautiful spiral arms can persist for billions of years. And then there's the supermassive black hole lurking at the center of almost every large galaxy. When these giants are actively feeding on gas and dust, they can release unimaginable amounts of energy. This energy blasts outward, heating up the surrounding gas and preventing it from cooling down and collapsing into new stars. In this way, black holes act as galactic thermostats, regulating the growth of their host galaxies. The cosmic web itself is not static, it's also evolving. Over eons, the filaments grow thinner as matter drains from them into the denser clusters. The voids expand and become even emptier. The overall structure of the universe becomes more pronounced, more defined. But there's a competing force at play: dark energy. This mysterious force is causing the expansion of the universe to accelerate. On the very largest scales, this acceleration is pulling things apart faster than gravity can pull them together, effectively slowing down the growth of new structures. Eventually, the cosmic web will essentially freeze in place. Galaxy clusters will remain bound together by gravity, but the clusters themselves will drift further and further apart from each other, becoming isolated islands in an ever-expanding cosmic ocean. It's a beautiful cosmic balancing act between gravity, which builds structure, and dark energy, which pulls it all apart. Galaxies also spin. The majestic rotation of a spiral galaxy is what maintains its flat, disc-like shape over billions of years. The secret to this stability, again, lies in its massive dark matter halo, which provides the extra gravitational glue needed to hold everything together as it spins. Elliptical galaxies, those big, fuzzy balls of stars, tell a different story. They are often the products of major mergers. Instead of rotating in an orderly disk, their stars move in random, crisscrossing orbits, like a swarm of bees. Star formation in these galaxies has mostly stopped. They are the older, quieter, more settled citizens of the cosmos. So, over cosmic time, the universe is slowly transitioning. It's moving from a chaotic, active, star-forming playground to a much calmer, quieter state. Fewer new stars are born. The stars that exist grow old, turn red, and eventually fade away. The universe as a whole becomes redder and dimmer. But even in this slow fade, the motion never stops. Orbits continue to evolve. Galaxies still merge. Gravity never, ever rests. By studying these motions, astronomers can map out the invisible. By observing how galaxies move within their clusters, they can calculate how much dark matter must be there, pulling the strings. It reinforces a profound lesson. What we can see, the light from all the stars and galaxies, is just the decorative foam on a vast, unseen ocean. The entire visible universe is riding on an invisible framework of dark matter that has governed its past and will dictate its future. Galaxies are not just random islands of light. They are deeply connected parts of a single, vast, intricate structure, bound by gravity across unimaginable distances. Their slow, graceful dance is what has sculpted the cosmos into the beautiful and complex place we see today. Thank you so much for joining me on this journey through the cosmos. If you enjoyed this video, please give it a like and consider subscribing for more deep dives into the universe. See you next time. To understand everything that followed, we have to go back to the beginning, not just to the birth of stars or galaxies, but to the moment when space itself first appeared. The universe did not begin as an explosion in space. It began as the expansion of space itself. In its earliest state, the universe was unimaginably hot and dense. All matter, energy, space, and time were compressed into a single, rapidly expanding point. There was no center, there was no edge. Expansion was happening everywhere at once. We call this event the Big Bang, but the name can be a little misleading. It wasn't a bang in the usual sense of an explosion. It was a transformation. Space itself began to stretch, carrying all the energy and matter along with it. In the first fraction of a second, something extraordinary happened. A brief but incredibly dramatic period called cosmic inflation. During inflation, space expanded exponentially, growing faster than at any other time in cosmic history. Distances smaller than an atom were stretched to astronomical scales almost instantly. Inflation is a powerful idea because it explains several deep mysteries about our universe. It explains why the universe looks nearly the same in all directions, no matter where we look. This is known as the horizon problem. Inflation solves this by starting them off close together and then stretching them apart faster than the speed of light. It also explains why space appears flat on large scales. Imagine an ant on a giant beach ball. To the ant, the surface looks completely flat. Inflation blew up the universe so much that our observable patch of it looks perfectly flat, just like that ant's view of the beach ball. And perhaps most importantly, inflation explains where the seeds of galaxies came from. The universe wasn't perfectly smooth. At the quantum level, there were tiny, random fluctuations in energy. Over billions of years, gravity would pull more matter into the slightly denser regions, and those tiny irregularities would grow into the vast cosmic web of galaxies we see today. After inflation ended, the universe continued to expand, but at a much more gentle pace. The intense energy began to transform into particles. First came quarks, the fundamental building blocks of matter. Then, quarks combined to form the protons and neutrons we're familiar with. Within the first few minutes, these protons and neutrons fused together to create the first atomic nuclei, mostly hydrogen and helium. But for the next few 100,000 years, the universe was a strange and opaque place. It was filled with a hot, glowing fog of free-floating electrons and nuclei. Light couldn't travel very far without being scattered by these charged particles, so the entire cosmos was like the inside of a cloud. Then, about 380,000 years after the beginning, a crucial change occurred. The universe cooled down enough for electrons to be captured by the nuclei, forming the first stable atoms. This event is called recombination. Suddenly, with the electrons locked into atoms, light was free to travel unimpeded through space. That ancient light is still traveling today. It fills every corner of the universe as a faint glow of microwave radiation, known as the cosmic microwave background, or CMB. The CMB is the oldest light we can possibly observe, a snapshot of the universe when it was just a baby. It's a faint echo of that early glowing fog. The cosmic microwave background is remarkably uniform, which confirms the idea that the early universe was incredibly smooth. But it's not perfectly uniform. When we look closely, we see tiny temperature differences, variations of just a few parts per 100,000. These tiny hot and cold spots perfectly match the predictions from the theory of inflation. They are the blueprints for all the structure in the universe. As the universe continued to expand and cool, gravity started to take over. The slight density variations in the CMB began to grow. Slowly, clumps of gas grew denser and hotter until, finally, the first stars ignited. This period is known as the cosmic dawn. These first stars were nothing like our sun. They were enormous, hundreds of times more massive, and they burned through their fuel in just a few million years. They lived fast and died young, ending their lives in spectacular supernova explosions. These explosions were crucial because they forged heavier elements, like carbon, oxygen, and iron, inside their fiery cores, and then scattered them across space. Without these first stars, the raw materials for planets and for life itself would never have existed. Supermassive black holes formed at their centers, growing by devouring gas and merging with other black holes. Over billions of years, simple, small structures merged and evolved into the complex, beautiful galaxies we see today. Throughout all of this, expansion continued, but the driver of that expansion changed over time. In the very early universe, the energy of radiation dominated, pushing everything apart and smoothing out wrinkles. Then, as the universe cooled, matter became the dominant force. The gravitational pull of matter slowed the expansion down. The expansion started speeding up again. We believe this is caused by a mysterious force we call dark energy. The balance between radiation, matter, and dark energy has shaped the entire history of the cosmos. Radiation smoothed, matter-built structures, and dark energy is now pulling it all apart. What's so remarkable about this story is how much of it we can verify. The cosmic microwave background gives us that perfect snapshot of the early universe. The distribution of galaxies on the largest scales, the cosmic web, reveals how structure evolved over time. When we put all the evidence together, from the lightest elements to the largest galaxy clusters, we get a single, coherent narrative of cosmic history that works with astonishing precision. When we talk about the universe expanding, we often imagine space just getting bigger. But expansion is only half the story. Alongside it, something else moves relentlessly forward: time. We all experience it as a constant flow from the past to the future, never reversing, never even pausing for a breath. And yet, here's the crazy part. The fundamental laws of physics don't really explain why time has a direction at all. Most of the core equations that describe our universe, from gravity to quantum mechanics, work just as well forward as they do backward. They don't have a built-in preference for a past or a future, and yet our universe clearly does. Think about it. Eggs break, but they never magically unbreak themselves. Stars burn through their fuel, but they never reassemble it from ash. We form memories of what was, never of what will be. This one-way street is what scientists call the arrow of time. And its origin story starts deep in the universe's earliest moments. Right at the beginning, the universe wasn't chaotic. It was actually incredibly ordered. All its energy was packed into a hot, dense state, but it was spread out very, very evenly. This initial low-entropy state is what made everything else possible. Now, what is entropy? You can think of it as a measure of disorder, but more precisely, it's the number of different ways you can arrange a system's parts without changing how it looks on the outside. Time flows in the direction that entropy increases. This isn't some rule imposed by time itself. It's just a consequence of pure probability. Ordered states are incredibly rare. Disordered states are overwhelmingly common. So, just by chance, systems naturally evolve toward whatever is statistically most likely. Imagine a perfectly arranged deck of cards. That's a low-entropy state. Now, shuffle it. It becomes disordered, a high-entropy state. And you could shuffle it 1,000,000,000 times and never get back to that perfect original order. The universe works the same way. As the universe expanded, gravity started pulling matter together. Now, you might think that clumping matter into stars and galaxies sounds like creating order, right? But on a cosmic scale, it actually increases the total entropy. Stars form, they burn their fuel, and then they die. Black holes grow by swallowing matter. Each of these steps creates more possible configurations for all the particles involved, increasing the overall disorder of the universe. So, the arrow of time is directly linked to the expansion of the universe. Without that expansion, the universe couldn't evolve the way it does. There'd be no steady increase in entropy and no clear direction from past to future. This connection also explains why our memories work the way they do. A memory isn't just an abstract thought. It's a physical record, a specific arrangement of neurons in your brain. The very act of forming that memory, creating that specific structure, increases the total entropy of the universe. To erase it, you'd have to reverse countless microscopic processes, and that is just astronomically unlikely to happen. We don't feel the arrow of time directly. We infer it from the changes we see all around us, from cause and effect, from aging and growth, followed by decay. On a cosmic scale, this arrow is written into the very structure of the universe. Galaxies form before they fade away. Stars ignite before they cool down. The universe began as a smooth, simple soup and has become incredibly complex over billions of years. Even black holes, the universe's ultimate vacuum cleaners, obey this principle. They have entropy, a huge amount of it. In fact, they might represent the highest entropy objects possible. When any matter falls into a black hole, the the total entropy of the universe increases dramatically. It's another step along this irreversible path forward. There's also what's called the thermal arrow of time. Heat always flows from hot things to cold things, never the other way around, unless you use energy to force it, like in a refrigerator. The early universe was incredibly hot. As it expands, it cools. Temperature differences across space flatten out as energy spreads. This leads to a fascinating, if a bit unsettling, idea about the far, far future. Eventually, the universe may approach a state of maximum entropy, a condition that scientists call heat death. This isn't some fiery explosion or a big crunch. It's a quiet fading into stillness, a state where there are no more temperature gradients, no energy available to do any useful work. Time would still exist, technically, but nothing meaningful would ever happen again. It's a bit of a grim thought, but it's also strangely elegant. The universe begins with perfect order, evolves through incredible complexity and structure, and ends in a state of quiet, eternal stillness. The arrow of time defines the entire narrative arc of everything that has ever been or ever will be. But this whole idea leaves us with one profound unanswered question. Why did the universe begin in such a low-entropy, highly ordered state in the first place? None of our current known laws of physics explain this initial condition. It's simply an observation about our universe. Some theories suggest a period of rapid inflation right at the beginning set the stage. Others propose deeper principles we haven't discovered yet, or even the existence of a multiverse where our universe is just one of many. For now, none of these ideas are confirmed. The origin of the arrow of time remains one of the biggest open questions in all of science. Still, the consequences are all around us. Because entropy always increases, stars have the fuel to shine. Life has the energy to emerge and evolve. Minds have the ability to form and think. Stories have a beginning, a middle, and an end. Without the arrow of time, nothing would ever happen at all. Time gives meaning to sequence. It allows cause to come before effect. It allows us to learn, to evolve, and to remember. It allows the universe itself to be experienced. So, the expanding universe isn't just growing larger in space. It's moving forward in time. Each moment is fundamentally different from the last. Each new configuration of the cosmos is less ordered than the one before it, but it's also richer in history. In our next video, we'll journey into the deep future and explore what happens at the very end of this arrow. What happens when all the stars die, the galaxies fade away, and only the most mysterious, deepest structures remain? What does the universe finally become when time has almost finished doing its work? Thanks for watching, and be sure to subscribe for more journeys into the cosmos. When we imagine the future of the universe, it's tempting to think in dramatic terms: explosions, collapses, sudden fiery endings. But the real future, the one written in the laws of physics, is much quieter than that. The universe doesn't rush toward its end. It drifts there, patiently, over timescales so vast they stretch the very meaning of the word future. The first great change will be subtle, almost unnoticeable. Star formation will slow down. You see, galaxies rely on massive clouds of cold gas to create new stars, and that gas is a finite resource. Over billions of years, it gets used up, either locked away inside existing stars or blown out into intergalactic space by powerful stellar winds and the activity of supermassive black holes. Gradually, the birth rate of stars drops. The cosmic nurseries fall silent. The existing stars will continue to shine, but no new generations will rise to replace them. Galaxies will slowly grow redder and dimmer. The brilliant, massive blue stars are the first to go, leaving behind only the longer-lived, smaller, redder stars. The universe enters what astronomers call the decline of the stelliferous era, the age of stars. Trillions upon trillions of years from now, most stars will be gone, not exploded, not destroyed in some cosmic cataclysm. They'll simply be exhausted, their fuel spent. The night sky, if anyone were there to see it, would hold only the faint, ghostly glow of red dwarfs and the dark remnants of stars long dead. White dwarfs will cool over eons, becoming cold, inert black dwarfs. Neutron stars will drift silently through the void. Black holes, however, will remain, the most enduring structures of all. Even the galaxies themselves will begin to lose their definition. The relentless expansion of the universe, driven by dark energy, will pull them farther and farther apart. Eventually, a profound isolation sets in. Every galaxy beyond our own local group will recede from view, disappearing forever beyond the cosmic horizon. The universe will become a collection of lonely, fading islands, each surrounded by an unreachable, eternal darkness. Then, even those islands will start to come apart, on unimaginably long timescales, far longer than any star ever lived. The delicate dance of gravity will unravel. The remaining objects, planets, dead stars, asteroids will be slowly flung apart by random gravitational interactions. Planetary systems will disintegrate, orbits will decay. All remaining matter will spread thinner and thinner, a faint dusting across the expanding void. This new epoch will be dominated by black holes. They contain much of the universe's remaining mass, silent gravitational titans in an otherwise empty cosmos. But here's the twist: even black holes are not eternal. Through a bizarre quantum process called Hawking radiation, black holes slowly, incredibly slowly, lose energy and mass. They evaporate. This radiation is so astonishingly weak, it's almost undetectable. For a black hole the mass of our Sun, the time it would take to evaporate is longer than the current age of the universe, by factors that defy comprehension. But given enough time, the future has an infinite supply of it. Even they will disappear. The very last black holes to go will be the supermassive giants at the centers of galaxies. It could take them up to 10 to the power of 100 years to finally fade away. That number isn't a poetic exaggeration. It's the cold, hard, mathematical reality. When the final black hole radiates away its last particle of energy, something profound happens. The universe enters its final state, a state of near maximum entropy. No more stars, no more galaxies, no more black holes. Nothing but a thin, uniform soup of radiation, elementary particles, and vast, empty space. This is often called the heat death of the universe. Not because everything becomes hot, but because all temperature differences vanish. Without a gradient, without hot and cold spots, no work can be done. Without work, no complex processes can occur. Time itself might still exist, but nothing meaningful would ever change. The universe becomes quiet beyond silence. No events, no structure, no possibility of observers. Now this future doesn't have to be tragic. It's neutral. It's the natural, ultimate outcome of expansion and entropy working together over infinite time. Of course, some theories propose alternatives. Perhaps the nature of dark energy will change, causing the universe to collapse back on itself. Perhaps our universe is just one in an endless cycle of creation and destruction. Or maybe, just maybe, new universes can be sparked from quantum fluctuations in the void. But for now, these ideas remain speculative. What we do know is this: the universe's future is governed by the same simple principles that shaped its past. Expansion continues, entropy increases, complexity arises for a brief, shining moment, and then it fades. And yet, within that brief window, something absolutely remarkable happened. Stars formed, creating heavy elements. Chemistry became rich and complex. Planets cooled, and on at least one of them, life emerged. Minds evolved. For a fleeting moment, the universe became aware of itself. We exist in a rare, privileged era. We're not too early, before the first stars and galaxies had fully formed. And we're not too late, after everything has faded into a cold, dark equilibrium. We live during the universe's luminous, vibrant middle age. That special timing isn't guaranteed elsewhere. It is not permanent. It is, by cosmic standards, breathtakingly fleeting. This perspective can change how we think about meaning. Meaning isn't something imposed by eternity. It arises within time. It exists precisely because things change, because moments don't repeat, because the arrow of entropy only moves forward. The universe does not promise us permanence. It offers us experience. Every single atom in your body was forged in the heart of a star that no longer exists. Every photon of light reaching your eyes has traveled across an expanding universe from a past that will never return. You are a part of a temporary, beautiful, and intricate pattern formed by ancient cosmic processes. And that pattern is precious, not in spite of the fact that it won't last forever, but because of it. But this journey into the far future leaves us with an even deeper question. Stepping back from the end, let's look at the beginning. Did the universe need a beginning, or could it simply be? That's what we'll explore next time. No matter how powerful our telescopes become, there are parts of the universe we will simply never get to see. The limits are woven into the very nature of space, time, and the speed at which any information can travel. The most basic boundary is the speed of light. We think of it as incredibly fast, but on a cosmic scale, it's a snail's pace. Light doesn't travel instantly. This means when we look at a distant galaxy, we're not seeing it as it is right now. We're seeing it as it was billions of years ago, when the light we're capturing first began its journey toward us. It's an observational boundary for any region of space beyond this horizon. The light from it hasn't had enough time to reach us since the Big Bang. Those places exist, but they are forever beyond our direct sight. The universe is expanding, and a mysterious force called dark energy is causing this expansion to speed up. Imagine two people on a stretching rubber band, walking away from each other. At some point, the band stretches so fast that no matter how quickly they walk, they can never reach each other again. That's what's happening to distant galaxies. Some galaxies we can see today are being pushed away from us by expanding space so fast that eventually they will cross our cosmic horizon and disappear from view. Their light will be stretched into oblivion, lost to us forever. This means the observable universe, the bubble of reality we can see, is just a fraction of the total universe. The true cosmos could be vastly larger, maybe even infinite, filled with countless galaxies and wonders we can never, ever detect. But the speed of light isn't the only wall we hit. There's also a limit called cosmic opacity. In the very early moments of the universe, it was a super hot, dense soup of plasma. Light couldn't travel freely. Photons were constantly scattering off charged particles, like trying to see through a thick fog. We cannot see beyond this era using light-based telescopes. The oldest light we can possibly see is the cosmic microwave background radiation. It's like a baby picture of the universe. But anything that happened before that picture was taken is hidden behind this opaque curtain. Gravitational waves, ripples in space-time itself, and tiny particles called neutrinos can travel through dense matter much more easily than light. Future observatories might use them to get indirect glimpses of those first few moments of creation. But even these messengers face their own limits and challenges. And then there are the practical limits. Stars don't live forever. Civilizations and the observers within them have finite lifetimes. We have limited resources to build ever larger instruments. The universe isn't waiting around for us to finish exploring it. It just keeps evolving. Even if we had perfect technology, we would still run into a wall of uncertainty. This is where quantum mechanics comes in. It introduces a fundamental randomness to reality. There are pairs of properties, like a particle's position and momentum, that you can never know with perfect precision at the same time. The very act of measuring something changes the outcome. So, at the smallest scales, there's a built-in fuzziness to reality that we can never get past. But these limits aren't failures. They are what define the structure of knowledge itself. They remind us that observation isn't a passive act of looking. It's an active interaction with the universe. And despite all these boundaries, the parts of the universe we can see show an astonishing amount of order and coherence. Everything follows patterns. Everything obeys physical laws. Things are connected to each other across unimaginable distances. The fact that we can figure out so much about the unseen from what we can see is truly remarkable. From tiny temperature fluctuations in that ancient cosmic light, we can reconstruct the entire history of the cosmos. From the way galaxies move, we can map the existence of invisible dark matter. Yet, beyond our best inferences, there will always be mystery. Regions of space that will never interact with our part of the universe. Histories that will never be known. Futures that will unfold without any witnesses from Earth. This realization is incredibly humbling. It tells us we aren't the center of the universe. We are not complete, all-seeing observers. We are simply participants, living inside a much larger reality we can only partially access. At the same time, these limits are what give meaning to the knowledge we do have. Our understanding is precious because it exists within constraints. The observable universe isn't a prison, it's a window. And through that window, we can see enough complexity and wonder to keep us busy for eternity. The unknown doesn't make the known less valuable. It frames it. It reminds us that the journey of exploration is endless, even when we know there are horizons we can never cross. In our next video, we'll turn our focus inward, not to distant galaxies, but to ourselves. We'll ask why a universe with all these limits would even allow for observers to exist in the first place, and how consciousness itself fits into this grand cosmic story. Thank you for watching, and if you enjoyed this journey to the edge of reality, be sure to subscribe for more.